Assalamualaikum warahmatullahi wabarakatuh. Good morning. Best wishes to all of us. Om Swastiastu, Namo Buddhaya. Dear sirs, organizers of the Isemantic Conference, and to the Honorable Mr. and Mrs. participants of the Isemantic Conference. My name is Krismaya Hardianti from the State Electronics Polytechnic of Surabaya and will present the result of the research I have done with Mr. Dindana Sudiarto and Mr. Epi Sunarno with the title Modeling of Overcurrent and Short Circuit Characteristic Curve in Digital Protection by ANFIS Method. The agenda for the discussion this time includes introduction, principal operation of the system, design and simulation result, conclusion, and reference. Currently, of the use of renewable energy is increasingly common as a substitute for fossil energy, such as the use of solar energy by using solar cells to produce electrical energy that can be applied at home. The system can produce energy that can be stored in the battery. The use of batteries to supply house loads usually occurs when there is no solar supply, namely at night, and has the potential to experience interference such as overcurrent and short circuit. So, to solve the problems that might occur, it is necessary to model the characteristic curve of overcurrent protection and short circuit so the system can protect when a disturbance occurs. Through this block diagram, it can be seen that the protection used is digital protection using the ANFIS method between the existing source and load. But this paper only discussed the simulation method used in the system block diagram, namely ANFIS, without implementation in hardware. The ANFIS method was chosen because when the processing is running, the model will work as a physiologic control with MF and the role of ANFIS learning outcomes so that it does not require a long time and is more efficient. Following the comparison between ANFIS and other methods that have been used in other research, namely Lagrange method and ANN method. Lagrange works by giving part of the point of the ratio data pair and trip time. Then we'll find other point that can represent the whole curve. However, Lagrange requires a long execution time because it has to use all pairs of curve data to get one model data point. The ANN algorithm works by learning data and then looking for the optimal value to minimize the error in the resulting output value. If the optimal value parameter is close to 0, then that is appropriate output value. However, the input learning data must have sufficient data. The data processing stage in the system have 4 stages, namely selecting the MF input type with the lowest error average value percentage in order to make the FIS result have a low error average value percentage, then data training, data testing, and data checking. To operate this protection system requires 3 understandings of digital protection: adaptive neuro-fuzzy inference system, and membership function. Digital protection was chosen because it has a higher intelligence than conventional protection. Digital protection is used as a controller processor and braking for algorithm and system, from reading current value, signal, and disconnects. In addition, this is a digital protection topology, which is an explanation of digital input and output protection and the algorithms that it processes. The digital protection program contains curve modeling with the ANFIS method. Curve modeling used two standards, namely IEC 60255 for overcurrent disturbance and IEC 60898 for short circuit fault. So the data ideal data as ANFIS input is obtained from the calculation and provisions of the standard. Here is an ANFIS architecture which consists of 5 layers. At layer 1, there is a classification process with nodes that serve to generate a degree of membership function called the premise. At layer 2, the node function to calculate the firing strength of a new membership operating two sets of each rule as the output of all incoming input. At layer 3, each node functions to calculate the ratio between firing strength in the rules that apply to HI rule to the total firing strength value as well, so that the result of this calculation are called normalized firing strength. In layer 4, it receives the output from layer 3 with the notation. At layer 5, there is the process of adding all the output of the result from layer 4. Here is an ANFIS flowchart, which is the algorithm operating produced on the MATLAB simulator that has been carried out. Membership function is curve that define each point in the input space to be mapped into a membership value between 0 and 1. MF can be formed by graphical representation. Graphical representation can be modeled into various types of MF input. In the following, there are learning data or ideal data derived from calculations and standards provisions used as well as reference to nominal current use. The ANFIS structure above has a 8 MF input type and 8 MF output type with a 8 rule base, and the fuzzy logic display below use the Sugeno type order 1. It has one input and one output, where the input is a ratio and output is a trip time. Following the forms of MF input before and after, as well surface before and after training for the trims and trumps input type, Gable MF and Gauss MF, Gauss 2 MF and Desig MF, Desig MF and PIMF MF. The following is the training result data for each MF input type with existing ideal data. The data from previous training are arranged in the form of characteristic curve for each MF input type. There is a blue line which is ideal learning data, and there is a circle symbol which is the phase result of each the 8 MF input type. The PIMF type has the most appropriate location with the reference line. At a percentage of the average error value of a type of MF input, the loss is PIMF with a value 0.9168%. MF input before training, testing, and checking has an ideal shape. However, after training, testing, and checking has changed its form due to a combine of learning data with data setting on M. The rule viewer before training, testing, and checking has a different output value. After training, testing, and checking with output value of 3.98. This is due a combine of learning data and setting data on MF. The surface before training, testing, and checking has a different shape from the surface after training, testing, and checking. Learning data is created as learning data for training, testing, and checking to be carried out. Approach training, testing, and checking have different approach form because of the different iteration process. Plot training, testing, and data checking have a location in accordance with the ANFIS output, so it can be concluded that plotting is in accordance with data learning. The following is the training data, testing, and checking the result of ANFIS TMS1. TMS 0.8, TMS 0.6, TMS 0.4, TMS 0.2, TMS 0.1. The following is a characteristic curve generated from training, testing, and checking data. It can be observed that the line symbol, which is the reference data, has the same location as the circle symbol, which is the ANFIS output data. So it can be concluded that the ANFIS output has a result that matches the reference. The following is a characteristic curve generated from training, testing, and checking data. It can be observed that the line symbol, which is the reference data, has the same location as the circle symbol, which is the ANFIS output data. So it can be concluded that the ANFIS output has a result that matches the reference. And it can be seen through the percentage of the average trip time error value with a value of less than 1% as follows. Conclusions. From the result of ANFIS with different MF type input, it can be seen that the large average error value is in the trim type MF input. The lowest value is found in the PIM type MF input. Therefore, is the simulation it used the PIM input type for the average value of ANFIS error testing. Result of training with the lowest error value is at TMS 0.1, testing with the lowest error value is at TMS 0.4, and checking testing with the lowest value is at TMS 0.4. The result of the percentage of the average error value for all TMS values from training, testing, and checking. Here are references that we use in this study. So many presentations from me. If there are shortcomings, my team and I apologize profusely and thank you.